Okay, comparison of the rates of nucleophilic substitution. The rate of nucleophilic substitutions depends on some factors. First is the types of halogenoalkane. Yeah, the tertiary halogenoalkane will undergo the nucleophilic substitution at a faster rate compared to the secondary and compare with the primary. So SN1 is the winner, yeah, since it proved the carbocation mechanism. So this will occur faster. Okay, the second effect, the second factors that affect the rate of reaction is the influence of the leaving group or the halogen. Okay, if we have Ci, the bond length longer compared than CBr, CCl, CF, then it will occur in a faster rate compared than the other halogens. Okay, look here. Okay, if the substitution reactions already occur, you would know that I minus or Br minus or Cl minus will be produced, right? Later on, we can see through the precipitation ratios with silver nitrate. Okay, so if you want to identify whether we have I minus or Br minus or Cl minus, you can check with silver nitrate solution. If it is formed yellow precipitate, then this is iodo. This is not too clear, yeah, not, yeah. But later on, we will see the color of the precipitates. Number 3, choice of solvent. So once again, if we use a polar protic solvent, so SN1 will be occur in the faster rate compared than if we use polar aprotic solvents. Okay, and then the nature of the nucleophile, this is number 4. Look here, the negative nucleophile, yeah, I mean the charged nucleophile is better compared than the neutral, yeah, the neutral molecule. So anions tend to be more reactive compared than the neutral species. So the rate of reactions with OH minus is faster compared than with H2O. Okay. In this case, Cn minus is the best. The second is OH minus, and then ammonia, and then water. Okay, why Cn minus is better compared than OH minus and H3 better than H2O? Look here, the second explanation. Among species with the same charge, a less electronegative is better than a more electronegative. Why? Since the nucleophile, yeah, tend to donate its lone pair, right? Okay, we want to compare about NH3 and H2O here. Once again, nucleophile tend to donate its lone pair to the C positive. If it is less electronegative, you know that nitrogen is less electronegative. That means it tends to donate the lone pair easier. Donate lone pair of electron easier. Compare then the strong electronegative atom. Okay, the strong electronegative atom will tend to attract electrons toward itself, right? Compare then to donate it. Yeah. So this lone pair electrons of oxygen is a stronger Hadley, yeah, by this atom compared than the lone pairs of electrons in nitrogen. So that's why NH3 is better nucleophile than H2O. Okay, once again, this is because the less electronegative atom can more easily to donate its pair of electrons as they are held less strongly. So that's why the best nucleophile is Cn minus, next OH minus, NH3, and then H2O. Okay, so there are 4 factors that affect the rate. First is the type of halogenoalkanes. Okay, and then the second, yeah, Okay. The second is from the living group. Yeah, if we have I is better compared than the other. Okay, and then the third is choice of solvent. And then the fourth is by the strength of the nucleophile. Okay. Okay, suggest expression for the following. Okay, let's discuss the answer. Why it is more useful compared than chloro compounds as intermediate in synthesis pathway. Okay, because this is because of CX bond breaks more easily in iodo and bromo derivatives, yeah. Then in chloro, so more readily undergo substitution reactions. So the point is because of iodo and bromo, easier to break, yeah. The carbon iodo and carbon bromo easier to break compared than the carbon chloro. So this is yeah, better, yeah, act as intermediate in synthesis pathways. Okay, the B, two compounds X and Y have the same molecular C4H9Cl. When each compound is reacted with dilute alkali and then silver nitrate is added, a white precipitate that darkens on exposure of air to air forms rapidly with X, but only slowly with Y. Okay, why? Okay, since this is a chloroalkene, so if the substitution reactions occur, okay, the Cl minus will be formed, right? And let's see about the types of halogenoalkane. C4H9Cl, there are four Cs. It can be the primary like this. It can be like this. Can be like this, or it can be like this, right? Okay, from these four, which compounds X and compound Y? Okay, once again, rapidly with X, but slowly with Y. So how do you think? Which X? X rapid, so X should be the tertiary, yeah? The tertiary halogenoalkane. This should be the primary. Okay, give explanation. X will be the tertiary halogenoalkane, which is this. Okay, because the precipitate formed rapidly. Once again, this is because of the tertiary halogenoalkane undergo SN1 reaction. Yeah, so that's why the Cl minus will be released rapidly and react with AgNO3 to form AgCl. Okay, you know the AgCl can turn darker, yeah, due to exposure to air. Okay, understand? So we are done with yeah, with this section. Yeah, and I will continue about the ratios of halogen alkanes at the next video. Okay, thank you for your attention. Bye bye.